Okay. Still section of 1, theory of heat, page 20. In practical terms, a piece of heating equipment is rated according to the amount of heat it will produce in a given time period. If the equipment had no such rating, it would be difficult for a buyer to choose the correct appliance. The rating of a gas or oil-fired furnace used to heat a home is permanently printed on the appliance's nameplate. Either furnace would be rated in BTU per hour, which is a rate at which heat energy is transferred into the structure. For now, it is sufficient to say that if a house loses on average 75,000 BTUs of heat per hour, the selected furnace should be rated at 75,000 BTU per hour. If a smaller furnace is chosen, the house will begin to get cold anytime the heat loss of the house exceeds the BTU/H output of the furnace. To describe the absence of heat, the term cold is often used. Because heat is expressed as a positive value in relation to no heat, cold is really an expression of comparison with no numerical value. When a person says it is cold outside, the term is being used to express a relationship to the normal expected temperature for the time of year or to the inside temperature. Cold is sometimes referred to as level of heat absence. 1.4. Conduction. Heat transfer by conduction can be explained as the energy actually traveling from one molecule to another within a substance. As a molecule moves faster, it causes the nearby molecules to do the same. For example, if one end of a copper rod is placed on a flame, in a short time the other end will get hot as well. The heat travels up the rod from molecule to molecule. Figure 1.8. Figure 1.8. Got the flame on the copper rod. Heat transfer by conduction is used in many applications. For example, heat is transferred by conduction from the hot electric burner on the cook stove to the pan or pot resting on it. Heat does not conduct through all materials at the same rate. Copper, for instance, conducts heat at a different rate than iron. Glass is a very poor conductor of heat. Touching a wooden fence post or another piece of wood on a cold morning does not give the same sensation as a metallic surface on a car or another piece of steel. Although the steel might feel colder than the wood, in reality the steel is not colder. Steel is a better conductor of heat than wood and as such causes heat to travel out of the hand at a faster rate. Figure 1.9. The car fender and the fence post are actually the same temperature, but the fender feels colder because the metal conducts heat away from the hand faster than the wooden fence post. Great, I just lost the page I was on. The sensation of cold is actually the feeling we experience when heat is leaving our body. When we get a fever, we often experience chills. This is partly due to an elevated body temperature that increases the rate of heat transfer from the body. The different rates at which various materials conduct heat have an interesting similarity to the conduction of electricity. As a rule, substances that are poor conductors of heat are also poor conductors of electricity. For instance, copper is one of the best conductors of electricity and heat, and glass is one of the poorest conductors of both. Glass is actually used as an insulator in some electrical applications. The properties of electrical conductors will be discussed in Unit 12, Basic Electricity and Magnetism. 1.5. Convection. Heat transfer by convection relies on a fluid flow, such as air or water, to move heat from one location to another. Many large buildings have a central heating plant that heats water and pumps it throughout the building to the spaces to be heated. Notice the similarity between the words convection and convey, to carry from one place to another. Convection can be classified as either forced or natural. Forced convection utilizes fans, blowers, or pumps to move the fluid, while natural convection refers to the fluid's flow, or its fluid's natural tendencies to flow. A gas-fired furnace is an example of a forced convection because air from the conditioned space is drawn to the application by a blower. The air then passes over the furnace's heat exchanger, which transfers heat from the burning fuel to the air. The air is then forced into the ductwork and distributed to the various rooms in the structure. Figure 1.10 shows this. Air from the room enters the blower at 70 degrees Fahrenheit. The blower forces the air across the hot heat exchanger and out into the structure at 130 degrees Fahrenheit. 70 degrees Fahrenheit from air. Yep. So yeah, figure 1.10 shows this process in which 70 degree Fahrenheit room air is entering the furnace, 130 degree Fahrenheit air is leaving, and the blower is creating the pressure difference to force the air into the various rooms. The blower, as mentioned, provides the forced convection. Another example of heat transfer by convection occurs when heated air rises naturally. This is referred to as natural convection. When air is heated, it expands and the warmer air becomes lighter than the surrounding unheated air. This principle is applied in many ways in the air conditioning industry. Sections of baseboard heaters are an example. When the air near the floor is heated, it expands and rises. This heated air is replaced by cooler air around the heater, which sets up a natural convection current in the room. Figure 1.11. Natural convection occurs when heated air rises and cool air takes its place. Natural convection, warm air out, cool air in. Warm air expands and it rises because it is now lighter than the rising air. Blah, 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 blah. 1.6. Radiation. Heat transfer by radiation can be best explained by using the sun as an example of the heat source. The sun is approximately 93 million miles from Earth's surface, yet we can feel its intensity. Heat transferred by radiation travels through space without heating it and is absorbed by the first solid object that it encounters. Radiation is the only type of heat transfer that can travel through a vacuum, such as space, because it is not dependent on matter as a medium of heat. Ooh, we're left on a cliffhanger. Okay, what was that? What pages were those? That was pages 20 and 21.